This video looks at the reuse of information within applications such as AVEVA Marine and some of our other Dabacon-based tools. Of course, reuse of data is such a big topic. We make so much information within one project that when it comes to beginning a new one, we really don't want to start again. Within this realm, we have many ideas within our software that can come under the title Design Reuse. That can be simply the creation of a corporate project through the full design reuse application, maybe Sisterships, again something simple like data files. So all of these solutions come together to really build up our design reuse strategy. So when we talk about reusable information and our solutions for working on it, we see that every design and production project creates and relies upon so much significant amount of information. And we have a number of ways that we can recreate it and reuse it, and we're going to order them in terms of their levels of complexity. So we can talk about corporate and standard projects, simple project replication, a copy so to speak, sometimes just taking the text definition of an element and copying that to another project using a simple file. We can catalog items that maybe represent design assemblies. We can use the design reuse application itself, but we can also implement other typical marine actions like Jumboisation. And finally in this video we talk a little bit about the Sisterships concept. So we can organize these as simple actions or solutions, some that may require some thought or preparation, and these are really self-contained solutions for working with information that's fairly self-contained. Then when we get to solutions such as design reuse and Jumboisation, these are ones that require planning. This is going to affect your design rules, particularly in the hull area, which relies so much on the idea of these rules, the rules capturing design intent. And finally, with the Sisterships concept, this is very much a consultative solution, something that we would really only work with existing customers. Primarily because this affects the way that a project goes. It may be a business enabler in itself. So these are kind of a hierarchy of different solutions that we can use with our software. We're going to do a number of demos during the video. We're going to have a look at copying of text data, cataloging design assemblies, and also look at using the design reuse application and the Jumboisation, which is reusing data but without copying between two different projects. So let's start at the simple end of the spectrum. So corporate projects are a great way to capture, say, equipment, piping standards in a project that is not necessarily part of the design project itself. As a separate project, it means that we can reference it into a new project without having to recreate that data. Of course, we can go on to create many projects with that, but the same solution may be used if you want to bring in third-party standards into your project, perhaps from a vendor or from a customer. It goes the other way too. Say, for example, you wanted to outsource work, say using AVEVA Global, you can send them your outsource party, your corporate standards, they can work with it. And using some of the database setup, for example, you can even tell that database to expire at the end of the project. Other simple solutions we have, there is obviously something like replicating the project. This is an operation which makes a direct copy of the project, but with a new name. So this is taking it one step further than literally copying the files themselves. It gives you the opportunity to rename and reorganize the project a little bit, but with all of the data inside it recopied and re-referenced within that operation itself. There's also a secondary option there to replicate the entire project structure, gives it a new name, but also references all of the corporate data, but the project itself is empty. So effectively you've got a blank sheet of paper to work with, but you have all of the catalog information that you've previously set up. So now we'll look at taking that a step further, the idea of using some data interfaces or working with corporate templates. So in the AVEVA Marine, E3D, PODMS style of application, and some of the 2D ones too, we have our design elements. And behind the scenes, although it may not be obvious, these are represented often by something that can be shown as a set of text rules, both for equipment, piping, and also the hull structural side. We have our long-running scheme files. Curved hull can be represented by XML text. They're just design rules. These capture our design intent, and if any changes occur, then these rules can be re-executed, and the elements can try and adapt to their new scenarios. As text, we can put this in a file. Files are really helpful, they're standalone, and we can take them to another project and bring them into it. We can, of course, email that data to someone else, another way of sharing data. But the key thing about these solutions is that when we get on to talk about the design reuse solution, this is something that works on top of these file interfaces. Makes a better interface for them to use for the user itself. Next, we'll come on to the standard model library. So this is another way of reusing data, but a little bit larger than just single items. So say, for example, you have made an engine room solution and you have a lube oil module, in this particular case, that you're fairly happy with. You feel that you could reuse this on many different scenarios. So you can select that area of the design and term it an item within the standard model library, an assembly in that respect. Now, if this stayed in your own project, the project itself, then it wouldn't be very useful. So there's no reason why you couldn't use some of the text interfaces to make this a corporate standard. And within the software, there's a nice bit of user interface design, a nice form to allow you to collect this data and actually create the necessary infrastructure within the project to allow you to reuse this. What this means that when you want to reuse this design, you go to the form, you list all the different libraries, you select the item you want, perhaps this lube oil module here, and you basically place that where you want it to. So it's creating an instance of that data. It's not referenced to that original data. If you decide to change the definition in the corporate database, it wouldn't change. So it's just really just instancing that into your design project. So in this demo, we're going to have a look at the standard model library. The standard model library is just a simple form interface where we can bring in previously collected designs that are stored in the database in a library area. So bringing open the form, and if we click on items, we can see different designs previously captured. In this particular example, we have some engine room libraries, one with 2 generators, one with 3 generators. Here we can see different engine room layouts, and the final one there we have a lube oil module. We can see that that contains different disciplines, some equipment, some pipes, demonstrating that this is can be quite a big assembly of different kinds of information collected so that it can be reused somewhere else in the future. So we're going to place this particular module, place it directly where its origin was originally created. That happens to be some distance forward of this design's position. You can see what that looks like in the tree. We see that we've got no textual naming. It's just a direct copy of the basic raw information that was there. It's not linked back to the original assembly. So we'll do an example of creating a standard model library element. We're going to reuse the bilge pump assembly that was developed for this project. We'll start by transferring this design to the common or corporate project. We're going to use what we know as the DATL file, a text description of the items in the project. So we transfer over all the members of the zone, and we just select a file that we're going to output this information to, a text file. So with the file saved, we can now transfer over to the corporate project, common project, and bring that data in. We'll just drag and drop that text file that we recently saved, and we can see the hierarchy is replicated beneath the site or zone we have available for us. So now we'll start the process of bringing this into the standard model library. This starts with a very similar form to what we had to place this in the project, and we can go through all of the items that we previously have in this library. In this case, we'll start by adding a new area. We're going to create an area for all of our little system modules. We'll just call it system modules. And then we'll create the standard model library item itself, representing the bilge pump. I'll just name it as bilge pump module. So with that done, we need to bring in the elements themselves. We'll just select the zone, apply, and that transfer then takes place. Once done, we can see the assembly appearing in the little view, preview at the bottom of the form. At this stage, the origin of this is just where it is in the project. To make this properly reusable, we need to set the origin so that it's relevant to the item itself. We'll use the snapping tools to do this. Now once we save, this module is pretty much ready to use. Of course, we'll get rid of the old module, the one we copied in, so it doesn't get in the way of any other stuff that we're working on. The module in the standard library is still visible for us to review. So now we've gone back to the original project, the instance, and we want to demonstrate how we can use the module in the standard model library if we've just created. So now we can see the system modules appeared. We can see it appearing in the preview. We'll bring in the entire design that we have here and place a number of these modules around the design. Again, we can use the snapping tools just to place the origin at different points, and we can replicate this as much as possible. Next, we'll have a look at design reuse. This takes this step of copying data a little bit further. It's very much about managing the data replication process. So with design reuse, we've already talked about that we have these file interfaces, and these are very good for capturing individual elements, but when you want to capture much more, then you have to deal with a lot more files perhaps. So what design reuse does is package these up into a transfer set. Effectively, it's a folder. That means that everything is captured together and everything is indexed together. For hull elements, design reuse takes this a stage further. Because hull elements rely on other entities, they reference them, you may find that you need to bring those across at the same time to make sure that everything can regenerate. The challenge is finding them. So design reuse introduces a tool where you can work through the references of elements and bring them into the transfer set as well. Of course, then the transfer set can be taken to another project. You can zip those files up, email them as you see fit. So the process itself works with a source project and potentially a target project. And the user interface tools, the forms, are similar in both cases. We see kind of a selection process where we select and build that data into a transfer set. That transfer set can then be read by the target project with a similar import style interface to bring that data into the project. Because everything is a text file within the transfer itself, this gives us the opportunity to maybe manipulate that data in the meantime. So we could apply something complicated like a transformation to shift the data in 3D coordinates, or we can make that really simple just by using a find and replace solution. Now we need to be quite careful with setting the expectations for design reuse. We are talking about exchanging design rules, we're not talking about exchanging typical geometric CAD data. Therefore, it's essential that the design rules can execute in the target project to be successful. If they are unable to, effectively, if you get rule violations, trying to correct these becomes a slow process. And this means that it's a lot about the quality of the original data. We really need to check the original data to validate it before we take that through into the new system. Of course, what we mean by this is bad data exported to another project is still bad data, so we want to avoid that as much as possible because it's going to be a bit of a headache to really make any sense of that. So what we would normally do is prepare by correcting errors, reducing the detail of elements to try and avoid too much manual correction. Once we get down to very small details, then the small changes that can happen between projects means that we've got to do quite a lot of work to re-correct these elements. So in this respect, my personal recommendations is perhaps think about going back to a basic design definition rather than trying to migrate or transform a detailed definition or production design definition where there might be a considerable amount of information that you'll have to change anyway if the design is going to change and update. So this is going to be the foundation of the demonstration that comes up. We have two ships. A 77-meter design that was set up to exploit the naval architecture and finite element applications within the AVEVA set of tools. And in the secondary case, we have a slightly longer design, although based on a very, very similar hull form. Fundamentally, the frame spacing is different in this one, and we'll see that we start to introduce a few more decks and compartments. So when we look at them in profile, we see that these are going to be the areas that we exchange, but when we map those bulkheads together, certainly at the bow, we have to transfer certainly the forepeak block ahead by one compartment. When we start to transfer our selected compartments, we'll see that they don't necessarily fit directly into the design. The new design has an additional deck, the new design is perhaps a little bit bigger. So we need the design rules to adapt to this new shape as we copy it across. In this second demo, we're going to be having a look at the design reuse solution. We'll be using this project as our source project, a basic design definition, not too complex, but good for showing the process. And this is our target project. It's just a surface at the moment with some deck infrastructure, but no structure directly, no hull panels. The blocks we'll be transferring are blocks 40, 50 and 90. Block 90 is the forepeak and that has to traverse one compartment over, whereas blocks 40 and 50 are directly where they lie in both vessels. So turning to the design reuse form itself, we start the process by drag and drop. This takes all the elements within that block into the transfer process. Now we may have more referenced objects behind the scenes, so we can ask the system to look for those referenced objects. So we have about 12 all told. Some are panels already included, some are RSOs, some of them are already in the target project, a different location, different design, but slightly different place. We don't need to take them. But what I'm taking through is block splits at 3 and 4, BS3 and BS4 respectively. So to build the transferred set directly, I just export. Give the transfer set a name. And now it's exporting all this data. And if you go to the folder itself, vet40, you'll see we have lots of files, numerous files per element, and these are indexed below to capture all the items that need to be brought in. So having created the transfer set, we can then move to our target project. Here we will open the design reuse application in exactly the same way, but it's going to be open in import mode instead of export. So we open the file up, and now it asks us to map any elements that it doesn't know about to new names. Some may get accept them as they are if they're being imported. In some cases we may map them to elements with different names but they already exist in the project when we want to meet them to a new geometry, for example. In this case we're transferring block 40 into the jumbo block. We just provide an alternative name. So in this first case, I'm going to manually import the block seams first. This is a good way of finding out if we have any particular errors. I'm also going to create a little 3D drawing on the fly so you can see the geometry appearing. Again, once it starts processing, it may ask me to map certain elements, so we're changing the name of the envelope. We'll map any decks that have been used as block splits to their proper deck geometry. So those are those two surfaces across. We will be able to see them in 3D. They happen to be there already. And now we can continue with the rest of the process. Again, we may have to map. So now the system goes through the process of executing the design rules in each element. Because there are references between panels and there will be maybe a number in many directions, it needs to run items a number of times. So while you may see failed on the first pass, this may be corrected at a later pass in the process. During this process, the screen might not update until work is done. So in this first example, we've copied across 83 items. We can see in the tree everything's got a green tick. We can drag and drop that items across. We can see those items in the 3D view. All nicely transferred. We'll now turn to block 50. This might not be so successful, so we're starting to change the location in the ship where it's happy to take some information from. Again, we'll check for any referred items. We'll save the transfer set. and we'll go to our target project and continue the process there. We'll pick up block 50, map these elements. In this case, we'll be mapping block 50 to a new block 50 that I'll create in a moment. This is because there are some shared panel names in block 40 and 50 that would end up going to the same panel if I try to put them all into Jumbo block. So that block needs to be created now. Block 50. We'll delete the representation of that block as we don't really need it in this demo process. And now we'll begin the import process. Again, mapping elements that need to be captured as something else. So that process runs. This time we're expecting perhaps a failure. We're starting to move away from the original location of these panels. Okay, so we're successfully imported 53 items, but one has a warning. We need to check up on that. So it would seem some design rules haven't executed as we expected. I know from previous cases of running this example that this particular bulkhead here, bulkhead 5, does not have the stiffeners that I expect. And an investigation led me to find out that what I need to do is do a regeneration of the deck to which these stiffeners are attached and bring in the stiffened bulkhead again. We'll bring in this bulkhead in simply as a scheme file because that's just an individual file. We don't really need to go through the whole design reuse process again. So we'll just go and find that panel in the transfer set, bulkhead 5 PP, and there it runs in. So success of the transfer is dependent on whether the design rules can re-execute. Next we'll turn to the forward block, block 90, which is in the forepeak of the ship. Repeating the process here. We'll just delete the information out of the reuse application and drag and drop 90. Export that. Now this experience in the target ship will be a little different. In the first ship, the block is located in compartment effectively 8 from the stern. Now it has to go to compartment 9. This means that bulkheads have a slightly different name, and I might have to introduce some new RSOs to represent the block splits. So I'm setting up this view so you can see what's going to happen. So this is bulkhead 9, and I need to introduce a BS9, block split 9, that's 200 millimeters behind this bulkhead. So I'm just going to do a copy. And in relative distance terms, we'll set this minus 200 back as a block limit. Okay. Now we'll get the block ready for reuse. Block 90, I'll need to create a new block, but otherwise we're ready to go. Again, we'll delete the representation of the block. Okay, so let's now import that. This was split on block split 8. We'll need to change that to block split 9. this bulkhead will also change from bulkhead 8 to bulkhead 9. So this is a big change, and I'm expecting quite a lot of failures. Effectively what we'll see is the block has been stretched from its original location to the bow. When I draw this, we can see that effect going on here. So we need to do more than just map the structure. We need to actually make a transformation of the data set before it's imported into the new project. So before we continue, we'll need to delete this data that we've just brought in. It's no good to us, and we need to manipulate it before we import it into this target project. So we'll make a quick delete. So what we're going to do now is update the transfer set, and rather than applying, say, a coordinate transformation, I'm going to do a very simple mapping, changing some text in these files from one position to another. It's the simplest solution that I could come up with. It's the sort of thing that you could use an application like Notepad++, but I don't have access to that. So in this case, I wrote a very quick application that would just go through these files, say for example changing here 108 to 124, and typically with all the other occurrences that I need to. So there's about 15 changes across the entire data set, just the frame references, no coordinate transformations. So now we'll bring that data back in again and import it. So now we're still getting some failures, but they're a lot less than what we began with. And when we drag that structure into the view, we can see that now everything is appearing in the right place. There are some stiffeners near the deck area that are run much further aft. It's because we haven't changed one of the coordinates, we focused on the frame references. We can see that some of the failures are probably due to the fact that we've got some holes falling off the surface, the geometry has changed, and if we start comparing the design, as we will see here, with the original, probably got quite a significant design change. Between decks 1 and 2, we have 6 kind of breastplates, whereas the target design really only fits in 3 plates with a hole. So it's quite a big difference between the two designs, and this illustrates that really what we're doing is transferring the design rules. If the design rules don't fit, then you need to make some design changes, but in the meantime the whole process of taking this geometry across is much quicker. Turning now to a typical jumboisation scenario, this particular case does not necessarily use the design reuse tools, but we could think that in certain scenarios we might use a combination of both to lengthen a design and then use the design reuse to insert new designs from other tools, other ships or projects in that process. So we might start by using project replication to build up a completely fresh design. And as I said, mixing and matching design tools is possible if you feel that that's necessary. So typical changes that affect a jumboisation would be updating the whole surface, changing the frames, perhaps inserting a new area, or alternatively making a geometric transformation to the whole data. In the example, we'll see that we have the original design used in the previous case, but what we're going to do in this case is add 5 meters below the bridge area. So this kind of solution requires a sequential update. The sequence is important. Depending on the order of the sequence, you can get a different result. So first of all, we need to think about whether the panels are placed by their absolute coordinate or by relative frame reference. If they are relative to frames and you move the frames, then the panels move. If the panels are stored with respect to their absolute coordinate, then if the frames change, the panels stay in their original location. And you may use this information to your own benefit, depending on what you want to do with the design. The first change we'll make will be to update the surface. Next, to actually impart the change onto the design itself, we would change the frames. This invokes the translation if we're using relative frame references, so that is where this information is key in this process. Once we've kind of applied the translation, we then need to go through sequentially and update information in order. So would start by updating any reference surface objects, RSOs, referenced by envelopes, update those envelopes, then update any RSOs that reference the envelopes, and then go through update the planar panels and update the curved hole sequence. Now, if you are planning on changing the frames after that to try and go back to a sequential framing system, then you could in addition change the panels then at that point to absolute frame references, reset the frames, regenerate the panels, and change them back to relative frame references if you needed to. So based on what you want out of this sequence, you can do quite a lot within that, depending on what your outcomes are for this process. In this final demo, we're going to be having a look at jumboisation, which is often a typical process that happens with ship design, extending an existing vessel to get a slightly larger vessel, but we don't necessarily use so much of the typical design reuse functions. So we're going to be extending the ship around 5 meters near the bridge area. So now we've moved to surface and compartment. Here we have extended the whole surface. You can see the original surface shown in the solid color, and the new surface is shown in transparent, and we've added 5 meters by just an extrusion of the parallel middle body midship section area. We'll simply release that into the design. This update also includes curves because some of the shell definition is linked to curves that we've supplied externally. Things like knuckles, transom, side of keel. Now back in the original application, we can see the original envelope that we started with, and also the new surface that we've imported in. So we can see at the moment that there's a difference, and that we now need to go through the process of completing the change and updating the structure as a result. We'll take a look at this from a drawing perspective. We'll take a look at the profile and look at how elements are changing slowly as we make these updates. So this is a view of the internal cellular structure. We can see that the whole surface has been extended, but the structure inside has not yet followed that update. In fact, we're going to make the transformation and jumboisation by extending the frames. So we're going to make a break at frame 57 and extend that by 5 meters. So these are the frame definition. We're going to add another line, starting a sequence of frames at what will be frame 58, continuing along to the original 120. We need to set that one back to 57. That's the end of the original frame sequence. This new frame sequence starts at 46,500, same frame spacing. But now the differences are calculated. The first frame sequence stops at frame 39,900, and the next frame sequence starts at 46,500, which should be a distance of 5 meters plus a frame spacing. So now when we draw the frames, we'll see a gap at that frame 57 location. The next step is to update our internal structure. First of all, we need to update the weather deck that limits the external envelope, because that envelope limits all the other surfaces, the reference surface within the project. We'll create another view that doesn't have all of the reference surfaces in to start with, so that I can sequentially show you what's happening. So these surfaces would normally have to be updated by changing the definition, because it's quite detailed, the change in shape, where it should happen. But in this case, I've saved these changes to external files, so I don't have to spend time demoing that. So if I drag that change in, we can see that all the forward coordinates have been shifted forward by 5 meters, and this allows me to limit the envelope. So if we take a look at that envelope here, all we need to do is go and update it. So once saved, that envelope recalculates based on the new surface information. I now need to update any other surfaces that need to be shifted. Again, we'll take these in from file. It's just coordinate transformations. So if I draw these into that view, you can see that there are some bulkheads that have shifted, the ones that I targeted in that file. There are other bulkheads or decks that need to be updated. We can just regenerate those. So at this stage, we've updated the internal cellular structure, the common reference model, upon which the panels in this project are based on. So the next step is to update the planar panels. So I'll create a 3D view here, and we'll look at this process occurring. These are our existing panels, and compared with the whole surface, we've got to make that change now. We can make that change all in one go. We just have to regenerate the panels using the design rules so that they update to the frame that they've been saved on. So we'll use a selection process to capture the whole block, and now that regeneration process will happen. So these are the errors that we've got from that process. We should investigate them, but we'll see that it's not too bad an update. The system now has to go through the process of saving, and we'll speed that up a bit here. So that update has now occurred. We'll take a look at what it looks like in the 3D view. We might see some failures in a different way because we can see the shading. So what we will see around the deck in the bow, that some of the deck panels have failed because the design rules have been violated. So I now need to investigate in that area how to correct those areas. So looking in a little bit more detail, we'll get a view of the deck. So here we've brought in the deck that those panels are based on, and we'll now bring in one of the panels as an example. So we see that this panel should be part of the kind of space that's in front of the location it's at. So we're just going to check some of the definition and update it. So that number needs to be changed to the second face, and we'll also remove some other information that is preventing the edges from updating. So it's a fairly simple change. We violated the rules, we need to correct them. Simple correction, and that panel can be updated without any problems. We'll move on, we'll leave the other panels for another time. The next stage that we'll go through is updating the curved hull definition. So we'll start with the seams. We'll also drag on the whole surface so we can see the comparison between the two and what we're doing. So to update, we'll just select all of these seams and let the system process them. There we go. Updated very quickly. We'll save and then move on to the shell plates. So selecting the shell plates, we'll let the system update those. This will take a while longer because it's also producing the production information at the same time. We will find some shell plates fail where the definition around the surface has changed too much for a simple update, and this is where the definition needs to be redesigned. Now moving on to the shell profiles. We will also get the surface again and do a selection to update all that data. So shell profiles are updated, we're saving, and what we could say is a matter of 15 minutes maybe, we've gone through the process of extending the ship, introducing a transformation, and then going through the process of updating all the information inside. We can see that at times it's not been 100% successful, but even if it's 99% successful, we'll find that that's a great benefit when we're starting a new project using the existing design, because that could save us literally many days of design work that we would need to get that information right. So finally, looking at the 3D view, we might pick out some errors. We can definitely see the area where we've extended the design, and there's our shell profiles, and we'll finish off with the shell plates. Finally, we'll have a look at the Sisterships concept. I would describe this as a business enabling data reuse, because it's really something that you would use over several projects or even several years as a strategy of how you're going to go about your shipbuilding business. Sisterships is not unusual. You start with a design, you deliver it, and then you need to carry on the through life aspect of that, where you may or may not use the original shipbuilding data. Now, if you're lucky to reuse that, or even luckier to have a range of classes or derivatives of a class, then you might make a number of changes and have to go through that process several times. The typical solution that is used with this case is the idea of a master design, and then derivatives of that. So that master will be stored in one version of a project, and there may be changes between the actual siblings of that project. We'd store those in differences. So this introduces the idea of project applicability, whether something in the master may not apply to a particular sibling, and we represent the difference in the database at the sibling level. This is always the way that we kind of talk and think about it, but in my experience we are often doing some slightly different examples. So in the particular case, a class design might start and evolve and produce a particular instance of that design over the lifespan of the class. I see many customers sometimes using this approach because it is slightly simpler. At the end of the process, you end up with one database per ship, and if there are any changes to that ship, it's simple. You don't necessarily need to think about the relationships to other designs. If you subcontract out any maintenance, you can do that through allowing them to use that single project, and they don't need to be considering the idea of what they would do and how they would propagate that information through to other projects if that was part of that process. So this is a very complicated process, and it's something that, while is powerful, we probably wouldn't introduce this to new customers until they had some experience with our tools. The reason being is that you can use a range of different solutions. AVEVA Engineering, Global, Design Reuse, they can all have a part to play in this process. So this completes this presentation, this video on Design Reuse, looking at a range of different options, starting with the very simple, moving through all to the quite complicated, business enabling solutions towards the end.